And greetings, everybody. We're live. Welcome to the Evidence and Reasons for the Christian Faith video channel. I'm Salvador Cordova, your host and owner of the channel. I need to just check the audio levels to make sure everything's okay. Host and owner of the channel. Oh, goodness. I already have a little technical problem here. All right. Good thing I check. So this channel is, as the title states, providing evidence and reasons for the Christian faith. I self-identify as a evangelical Christian, evangelical Reformed. People will ask if I'm a Calvinist. I'll say I don't identify as a Calvinist. I'm a Bibleist. That means that if there are words in the Bible that are there, I'll accept it. So if it uses the word election or predestination, I accept that. I don't really have a system of how to reconcile some of the apparent conflicts. I'll just leave it at that. If the Bible teaches it, I'll say I'll accept it. I don't necessarily understand how I can reconcile some of the ideas. I'll just say it's there, and maybe it's beyond me to understand. The other thing I need to mention is I am a young Earth creationist now. I believe the cosmos. I'm also a young cosmos creationist. I believe the cosmos is young. I used to be a theistic evolutionist. I was raised in the Catholic Church before becoming Protestant. That's where I believed in evolution for a season in my life, and I no longer do. And I have 5 science degrees. I work for a world-famous geneticist. All this to say is, the reason I'm saying this is some people have been wondering if I'm an atheist or if I'm even a creationist, because I've been very critical of other creationists, particularly Kent Hovind. And just because I'm a creationist does not mean I will not call out other people that claim to be creationists and Christians. If their science is bad or anything else that they're doing, I consider as bad and harmful to Christians in particular, and secondarily to creationists. So I just, that's why I've had a little bit of a preamble. Most of the audience is starting to gravitate. This channel tends to attract graduate students in science and professors and professional researchers. So some of the material is very scholarly, and that's a respectable way of saying really nerdy. Some of the material here that I talk about is just brutal. It's the sort of thing we'd expect graduate students and professional researchers to be talking about as it relates to creationism and intelligent design. And so we occasionally have topics that are accessible to other people. Like last night we talked about abuse of women in the church, and because Cindy Lincoln is a frequent co-host on this channel. She suffered a lot of mental and clergy abuse at the hands of Kent Hovind, and some people really didn't like me talking about that topic, but I felt it was my responsibility because Cindy is an important part of this channel. One reason I was late, I was actually somewhat chewing her out tonight because she got some of her thermodynamics wrong. I was really upset about that, and I said, well, I'm not going to send her a nasty email about thermodynamics. I said, I don't want to hurt her feelings. She's going through enough. So I gave her the courtesy of calling her and saying, Cindy, it's not the way to go about defending creationism using the second law of thermodynamics. I said last night, I'm usually a patient guy, but I have a short trigger when it comes to bad science. That's because it's just like, okay, in mathematics, if you type a negative sign when it's supposed to be plus, things can blow apart real fast. And that's just the way, when it comes to science, if there are things that when we're making scientific arguments, it's very easy to just say the wrong word and the whole argument is just blown apart. So it's one thing I'm really persnickety about. And she said, "You did say you have a short trigger on that." And I said, you bet I do." So I had to try to hold my temper and say, "Okay, Cindy, just don't use those arguments." And I had to try to explain to her what I felt are better arguments. So I apologize for being late. That's the nerd side of me, just coming through. And Cindy needs a lot of support during this time in her life as she's recovering from really just an ordeal. And last night I tried to hand her off to a community that will be better equipped to help her through her problems, hopefully. Jennifer Greenberg, and then a community of women who've been abused in the church, and all sorts of levels of abuse too. And I hope that they can help her, and hoping and praying for the best for her. So with that, I'm trying to get back to business. One reason I'm having this reading of this nerd topic is, yes, thank you, nice to see you, Wesley, and thank you, Patrick Alexander. Tomorrow night, CRISPR-Cas9, who is a PhD student, I believe, and he's also an assistant professor, very smart. He'll be coming on the channel to talk about junkDNA with me. Now, let me say this. There are areas within intelligent design and creationism that are not as strongly argued at this time as other areas. So what do I mean by strongly argued? We can, creationists and ID proponents together, they've definitely got the high ground. They've obliterated the abiogenesis, naturalistic abiogenesis argument. And partly because the secular community's starting to realize the problems with abiogenesis. It used to be, when I was going through school, they said, Uri Miller, this is how life arose, and there was optimism that we'd solve it. And then the problem got more difficult, and people like Fred Hoyle, very good physicist, pointed out the problems. He came up, in the prestigious scientific journal Nature, he said this is like expecting a tornado passing through a junkyard and building a 747, the difficulty of forming the first cell. He therefore invoked space aliens, which we laugh at, but that's the severity of the problem. That if the problem of the first life is so severe at this point that they have to appeal to extraterrestrials, then you know the theory is in serious trouble. And so it's gotten, and that was like in the 70s, 80s. Nowadays, they're invoking multiverses. Anything but God. I mean, there are peer-reviewed papers now coming out advocating that. So creationists and ID proponents were definitely on the, I'm declaring victory on that. I don't expect we're going to be overturned. Unfortunately, on a more obscure topic, but I think also effectively, we can also argue against eukaryotic evolution. We own that argument. We own it so bad that the other, half the time the other side doesn't even know what we're talking about. It's so over their head. I've known that in my discussions and debates with the other side. It's like, huh? They wanted to talk about chimp human. They thought I'd come to the table and argue evolution over chimp human common ancestry. And unfortunately, a lot of creationists play right into their hands. I said, why are you attacking the thing that they're strongest at? Attack them where they're not even looking. with your strongest argument against evolution, and that's eukaryotic evolution or individual molecule evolution like topoisomerase. You're just going to obliterate them. They won't even want to show up and argue with you. They won't know what to do. Or I'll say, how about nuclear pore complex evolution? How about membrane-bound organelle evolution? How about localization and transport? And like most of creationists, like I don't even know what that is either. It's just like, okay, this is why you need to learn the science. There was a tactic, the most famous, the #1 fighter pilot, Eric Hartman. Sadly, he fought on the wrong side in World War II. He fought on the side of Nazi Germany, but he was regarded as an honorable soldier defending his homeland. He wasn't viewed as a diehard Nazi. He was forgiven. He became a general in NATO after the war. That meant he joined the Allies. But a fighter tactic that he used, 80%, he shot down 352 opponents, 352. Okay, you've heard about the Red Baron. I think the Red Baron had only like 80 kills. This guy had 352 kills. If you see pictures of him, he looks like the sweetest smiling guy. It's like, yeah, don't be fooled. He's a killer. He probably is a very sweet guy personally, but up there in the air, he was just deadly. And what was his key to success? 80% of his kills, the other guy didn't even know he was there. And so the creationist argument that will be most effective against evolutionists is you're going at them where they're not expecting. Do not debate someone like Erica on this, on chimp human ancestry. Don't. Why? She's a professional primatologist. And we have creationists who are not specialized in that field trying to go up against her and just like, why? You have so many other avenues. Okay, so what Eric Hartman realized, okay, you have kind of the cockpit on top of the airplane. You can only see up above. Why do you attack where the other guy can see you? You attack him for where he can't see you. So what Eric Hartman would do, he'd fly really low and these airplanes would be there. Okay, so you have the enemy airplane here. Eric Hartman kind of just sneaks up behind him here where you can't see him, comes up and gets really, really close. So close that there's no way he could miss once he presses the trigger. Presses the trigger, doesn't miss, he's not in a dogfight, and then he runs away. I know that may not seem really sporting or skillful, but he said, well, he doesn't engage. That's the other thing. As a fighter pilot, as brave as he was, and he was very brave, he never engages in a fight he doesn't think he's going to win. You got to know when to run. And there were some also very successful American fighter pilots like Donald Flash Gordon. And he said, this is the way to win the war. You don't dogfight. You come up where he can't see you and you blow him out of the sky. And so I was getting kind of irritated with Cindy. I was just like, Cindy, stop. And I apologized last night because I sent her a pretty nasty letter. She said, you really hurt my feelings. I said, I'm sorry. I said, don't argue chimp human ancestry. It's going to be fruitless and pointless. What do you accomplish? I'll tell you why. If you're a young earth creationist, argue young earth creationism. Because if the earth and fossil record are young, there's no common ancestry. Done deal. Why are you going to be arguing about all these fossils and all these progressions? It's a done deal in 1 minute. Okay, so then they'll say, okay, there's no common ancestry if the fossil record and life are young. Say, okay, now we can build on that. We can argue that. So one of your arguments is genetic entropy. Another are Evidence is the fossils are young. So what does that have to do with the discussion tonight? We're going to be talking about junk DNA. And the reason I'm having a discussion and genetic computers. Tomorrow, I'm inviting CRISPR-Cas9, and if Dr. Dan wants to come, I sent out an invitation to him too. But it was really CRISPR-Cas9 I wanted to talk to because I don't get to talk to him too much. And Dr. Dan has frequented this channel. And I said, okay, I don't feel that I could win the argument over junk DNA like James Tour would beat Dave Farina's head into the ground. Because partly, it's not just because I don't know, it's really, I don't think we're at the stage that we have enough experimental and observation evidence to really definitively argue. But I think we could put up a pretty good fight. And why is this important? Dan Grauer and the evolutionary biologist in his camp have said, if ENCODE is right, then evolution is wrong. If ENCODE is right, then evolution is wrong. The ENCODE project, which is a $500 million project, and the follow-ons are, if you add the original ENCODE plus follow-ons, it's probably $1 billion of research at this point. They have come out and said 80% of the genome is functional. They got a lot of pushback from people like Grauer, and they kind of backed it down a little bit, tempered their remarks, and I just wanted to say, why don't you guys back down? He doesn't have anything of real experimental proof to say one way or the other. It's none of his business. You're the medical researchers that are trying to solve cures for human diseases like cancer, and you know 90% of the heritable diseases or problems in, like even with cancer that may not be immediately heritable, it's because of dysfunction. It's associated with all these cellular dysfunctions are associated with the non-coding DNA. 90%. You have the high ground. You don't need to bow down to some evolutionary biologist saying you can't say that. I mean, what does Grauer have? Does he have experimental evidence? How is he going to prove that it's absolutely junk? I mean, is he going to explore every molecule before he makes that? He'll say, oh, that's what evolutionary theory says. And it's really kind of funny because there's some evolutionary biologists that have a different opinion. So why are we fighting over this? This is one battleground. As I feel we've definitely crushed abiogenesis. If they wanted to fight on eukaryotic evolution, they're going to be crushed, and they don't want to debate that. They'd rather debate Kent Hovind, sorry to say, because he's terrible. They're not going to be able to successfully debate on eukaryotic evolution. If we had, if we had an extended debate on this, they'd be absolutely obliterated. So the next frontiers that are there are genetic entropy, and the junk DNA argument ties into that. So this is kind of a long review where the debate is just setting it up for tomorrow night. We're going to talk about this. 12 years ago, there's a lot of, even longer than that, 2006, a lot of people were, there are a few people who are saying, DNA is mostly junk in humans. And particularly the Alu elements, which are 10 to 11% of the human genome. And Francisco Ayala in 2010 was coming out and saying, what an incompetent designer, if there is one. He made Alu elements. This is all junk. Will we find function for the Alu elements? And he said, not likely. Well, right at that year, papers were coming out talking about function in the Alu elements. in a conference in 2016, Dr. Sanford was saying, you know, if there's anything that would make me go back to being an evolutionist, it'd be the Alu elements. He said, this is hard. And right after the conference, he said, Sal, I want you to look into that. And I was like, thanks, boss. You know, and I said, Lord, I can't solve this. It has to be, you have to deliver for me. And it just so happened that the papers were right there. I spent a month collecting them, and I sent Dr. Sanford a 7-page report. He shrunk it down to 1.5 pages and put it in Contested Bones with his co-author, Chris Roop. And I'm like, John, this is such good stuff. You only gave me 1.5 pages. And we said, you know, and I was like, okay, you know, there'll be another day. There'll be publications on this. And so now this is my chance to articulate the case on the Alu elements. But in 2020 and beyond, Alan Herbert was able to publish in Cell, which is a very respectable journal, prestigious, and Royal Society Publishing proceedings, the equivalent of our National Academy of Science there, Royal Society Publishing. And my jaw dropped. The Alu elements that were so maligned by evolutiologists like Francisco Ayala, John Avai, T. Ryan Gregory, Larry Moran, who's not an evolutionary biologist, Dan Graur, and they're just mocking and denigrating, and they're getting away with this for 30 years, you know, up until 2006, and then they're getting a little pushback, but they still kept going with their mantra. And then 2012, they were just on a tirade because ENCODE was basically suggesting that Alu elements are functional because they get transcribed. And they kind of came up with some clever counters saying, oh, these are spurious transcriptions from the Alu sites. And you know, they don't do anything. Well, but then in 2016, we started to get stuff with adenine to inosine editing studies. We didn't quite know what that meant, but if that didn't happen, the creature died. And these editing things would happen in the Alu element RNA transcripts. Okay, I'm getting really technical. I told you this is a nerd torture session. In 2020, more studies came out. They began to connect the dots. And so now it's been almost 45 years that they've just been gloating and mocking, and they could see warning signs that, you know, Larry Moran and company were just insulting people that thought junk DNA wasn't really junk. They've been getting away with it, but I think that time's coming to an end with what basically the review papers that Alan Herbert has put out. The experimental evidence is devastating. Now, you know, the battle is far from won, but I call this like the Battle of Midway. You know, the end is in sight at this point because it's a matter of now just connecting the dots. So what I mean that the battle's not won, we've found enough, we've characterized enough systems where the Alu is important. There's every reason to expect it'll be used in like manner in other systems. So like, for example, we've characterized a few proteins in the human proteome. And we'll expect the rest of the proteins are functional. And most of them we've not characterized what they do. It's so hard to characterize just one. And for those of us who, for those of you who watched the topoisomerase video, you got to hear Joe DeWeese's webinar, and he's studying that professionally for 20 years. And there are hundreds of people studying it their whole professional life, and that's just one protein. Are we going to just say, well, we're not going to assume that the rest of the proteins are functionless because we haven't characterized them? That'd be a stupid attitude. And so in like manner, just because we haven't characterized every function of every Alus segment or every non-coding DNA segment, we're going to assume it's functionless. That's kind of stupid. Why don't we wait and see? Instead, the evolutionary biologists in Dan Crowder's camp and Larry Moran's camp are just really eager to push the narrative this is junk. There are two reasons for that. There's just been the general tendency to say that life is incompetently designed, it's stupid, it looks like really clumsy. Because the last thing that they want to say is this looks really elegant. This looks sophisticated. It looks brilliant. It looks perfect. Because then you have to contend, how did that arise? And if natural selection can't explain it, that's going to be a problem. So that's one. The other thing more formally is the mutational load, which Dr. Sanford has harped on. If the genome, one way I define complexity is the number of things that can go wrong. So if you have a small password, it's low complexity. If you have a long password, it's high complexity because you have more letters that you can go wrong when you're typing them in. And I would just extrapolate that idea to biological complexity. The more things that can go wrong. The more things that can go wrong, it would imply that there's a point where there could be so many things going wrong that when you have 100 mutations per generation per individual, there's no way you're going to be able to clean it out. Because if the next generation is more damaged genetically than the parents, then there's no way natural selection could clean that out. So even if there's survival of the fittest, it's really survival of the fittest peers, not survival of the fittest in terms of the parents and the children. Because if the fittest genomes were with the parents and they're stopped reproducing, or not, if the fittest genomes are the parents, but then their children on net average do not have their parents' genome, then in a sense, the fittest actually do not survive if we're looking at genomes across time. Survival of the fittest, as defined by Dorman and Spencer, is really horizontal, the genomes among peers. And that's the flaw in the thinking. And it took me a while to realize that. You see, it ends up being a rhetorical trick or a rhetorical delusion. It's not rigorous. It's not rigorous. So that's the importance of this discussion. So with that, as we were talking about, we don't know enough to say there is or isn't. I would say at this point we know enough to have a strong suspicion the evolutionary biologists are wrong. And that's the topic of the argument that I'm trying to make. It's hard to successfully argue for junk DNA. It could easily be argued that data are inconclusive at the moment. Yes. Yes. You see, the other side is in a position you absolutely don't want to be in. They're being presumptuous, and they have to be right, because otherwise evolution is wrong. The medical researchers, it's like, well, we're trying to solve human disease. We're not going to argue about evolution. We're trying to find cures for cancer. Just buzz off, guys. Of course, the creationists can bide their time on this because it is inconclusive at the moment. The evolutionists, all they can argue for right now is that if junk DNA is functional, then evolution is wrong. And the reasoning is, well, since evolution is right, then junk DNA must be functionless. Okay, that's a simplification of the argument. Dan Grauer's own words: if ENCODE is right, that is, if ENCODE is right about junk DNA being not junk, that it's 80 to 100% functional, then evolution is wrong. In fact, what's really kind of funny is encode only needs to be 10% right. And I've walked through the math here. We don't even need encode to be 100% right. It only needs to be 10% right, and evolutionary theory is wrong. And I've walked through the math here, a paper we released in 2021 with the criticism of the evolutionary definition of fitness. We can demonstrate that encode only needs to be 10%. You only need 10% of the genome to be functional. And I think most people would agree at least 10% has to be functional, because if it's not, you're going to argue that something as complex as a human being is being implemented by less than 700, 800 megabytes. That's kind of hard to believe. So I wouldn't want to be on their side of the argument. They can build all the phylogenetic trees that they want. They have a mechanistic problem. You know, I build phylogenetic trees, but I'll say it's a non sequitur that it explains the origin and maintenance of complexity. And then when I ask how do you prove this evolved, they'll appeal to a phylogenetic tree, and I'm just like, don't you see there's circular reasoning here? You're assuming the phylogenetic tree proves evolution, but you have to demonstrate that the phylogenetic tree is an adequate mechanistic explanation in terms of the biophysics, the biochemistry, cellular biology, statistics, and it falls, too much circular reasoning there. So I'm just trying to set this up. So Wesley has a good insight here. People argue that life can be created from its components through natural laws of chemistry. But isn't there a law for that, law of biogenesis? There is, but there's a better one. It's Virchow's principle. It's called, look up in Google, or look at the Wikipedia entry for cell theory. Cell theory says that all cells come from pre-existing cells. All cells come from pre-existing cells. There might be some nuances in the wording, like all cells come from the division of other cells. Or you could say the budding off, or whatever. I like all cells come from pre-existing cells. That was Virchow, who actually got it from someone else, but he got most of the credit, historically speaking. Hang on. If there are mods out there, hang on. Whoever took care of that, thank you. And Wesley, I'm going to make you I think you're a moderator. Thank you if you whoever took care of the bot. So you could say that is a principle. That's in my biochemistry textbooks. I mean, this is what's kind of funny, is there you have it right there, that something really special has to happen for the first cell to arise. Because if all cells come from pre-existing cells, where does the first cell come from? And that's the problem of abiogenesis. Of course, later in the textbook, they'll say this is how the cell evolved, but that doesn't agree with our observations. And so how do we criticize it? That it won't evolve naturally. That's what James Tour did. He pounded Dave Farina into the ground, and that had to be the most beautiful takedown I've ever seen on the internet. It was delightful, something we should celebrate. So greetings also. So now this is the third part. Is this the third part? Yeah, part 3 of reading this Royal Society paper that's going to take apart one aspect of the junkDNA argument from the evolutionary biologists. That is, this paper is by Alan Herbert. He's definitely an evolutionist. He's actually saying, oh, look, these genetic computers are so sophisticated. Natural selection had built it. Okay, so this is what's really bad, is in the larger community of scientists who are both pro-evolution, you have one group that'll say DNA is functionless. That's proof of evolution. And then you have another camp like Alan Herbert who'll say DNA is functional. Evolution did it. Okay. So you have one group that said DNA is junk. Junk DNA is junk. They're, evolution did that. And then you have the other camp that says junk DNA is not junk. Evolution did that. So I just want to make it clear, Alan Herbert is arguing the latter, that junk DNA is not junk, but evolution did it. Now, he's not, I need to point out, he's not an evolutionary biologist. The evolutionary biologist recognized the problem. Alan Herbert is I think, he's a professor in pharmacology. So he's some sort of biochemist, definitely. And you're going to, as I read this paper, you're going to realize this guy's extremely bright. So guys, I spent 36 minutes kind of trying to make this as accessible as possible. Strap on your seatbelts. This is, as I read the rest of the, this is already part 3. I'm not even, let me see. I'm not even a third part through the paper. And I'm reading this, Googling the terms, trying to understand. So I'm just gonna keep reading in preparation for my talk tomorrow. What's my talk tomorrow going to be with CRISPR-Cas9 and possibly Dr. Dan? It is not to settle the issue. It is to gather information from both sides of the argument. Obviously, my biases are that it's functional, but I will admit we don't have all the data in as much as we would like to make a James Tour type beatdown. Yeah, James Tour is the platinum standard for beating down the opposition. But I'm planning to make talks to Christian faculty at both religious and private institutions, Christian faculties and researchers and graduate students at religious and also secular institutions. And I have to give them, it's my responsibility to communicate what I think is true, but then also identify this is from a limited data set, we don't know as much. And I'll pass on what I think are credible counter arguments that they should be aware of. So, but I think it's still important that we don't have to wait to get everything right. Nothing in life, many decisions in life we don't make with all the data. We usually make a lot of decisions with less data than we would like to have. That's just the way it is. But we don't just throw up our hands and not try to gather some. And so with that spirit, I'm going to read this paper. And as I've been going through Alan Herbert's stuff, I said, this is pretty powerful. I would not want to be Dan Grauer or Larry Moran and just waiting for this industry to collapse, because it is moving like a steamroller at the pace that this knowledge is coming through, because we have advanced experimental techniques. So the reason this debate continues to move forward in favor of ID proponents is we're able to conduct better experiments, make better observations, gather more data and interpret it than we ever have, and we're going to continue to. I expect that. Everyone's optimistic. We're going to continue to gather more data, and that's the important thing. So I don't know how long tomorrow's talk is going to be, discussion. It could be pretty long, but tonight I'll just, this is preparation partly for tomorrow, and then really more importantly for my talk before the Christian faculty and researchers. So let's dive into it now. So where did we leave off? We left off here. It took me an hour to read this paragraph, which I'm going to read now. And I'm sorry that, I've tried to explain things as I read, and I don't think I have that luxury. Otherwise, it's going to take forever. But as I read it, even if you don't understand, one thing you'll see is that so many things connect together. Just like if you look at a car and you see all the parts, you may not be able to name all the parts or understand what they do, but you can get the sense that this is very important for function. So, maybe just leave it at that. If you don't understand, just try to appreciate you're listening to how the complexity is laid out for this genetic computer. So where does it say that this is a genetic computer? That was actually the title of Alan Herbert's other presentation, where he kind of gave an overview. But if you're seeing how this is laid out, it really is describing parts of the genetic computer, but it is so deep in the weeds. Okay, so let's go. Let's go, Brandon. Studies have revealed that ADAR Z-alpha binds a number of genomic sites. ChIP-seq based on an ADAR Z-alpha dimer identified a total of 391 Z-forming sequences, mostly 46% in promoters and associated with active histone marks such as H3K4ME3 and H3KAC. Last time I described what all this means, and I'm not going to go there again. I need to point out something, though. The other side will say, well, you only have 391 sites. And I'm just like, well, we only studied 100 different cells out of 100 trillion. So if they say you should identify the whole genome, I'm just like, bud, most DNA is shut in most cell types. It's shut off. 90%, some cells, 90% could be shut off, and you're only expressing 10%. There's no way that we can rule out that it has no function until you've explored all 100 trillion cells in all cell phases and all stages of development. It could be there, you're just not detecting it yet. So I'm just putting that out there, and because I can, I've dealt with these critics forever. I know what they're going to say. It's like, well, that's hardly anything, 391 sites. I'm just like, yeah. 391 sites and 0.000% of the genome has only been surveyed anyway, in terms of all the cells in the human body. I'm just like, there's reason to think that the more cells and cell phases and cell types where you have access to, where we could actually look, we'll start to find more. Just pointing that out. And someone that would be actually a good study to demonstrate. Oh, as we sampled more cells, the number of Z-forming sequences we find grows. I'm just like, okay, that's going to tell you something. That's a testable prediction. So let's go on. Let's get going. Let's go, Brandon. The MAP genes are enriched for replication-dependent histones prone to citrullination. Citrulline is a special amino acid. Cell cycle factors, transcription factors, and topoisomerase. Oh, I love that term. Topoisomerase 3A, which is essential for resolution of D-loop recombination intermediates. Okay, now I'm going to pause just a little bit. I need to find out what topoisomerase 3A is. So let me look here. I'm going to look up what topoisomerase 3 alpha is, if you will indulge me for a little bit. I work on 2 alpha. I don't work on 3 alpha. All right. I'm just trying to see if it works with mitochondria. So topoisomerase 3 alpha mitochondria. This would be interesting. mtDNA, replication and transcription require DNA topoisomerases as cofactors. 3 topoisomerases have been found in mammalian mitochondria. 1, 2 beta, and 3 alpha, but their biological functions remain unclear. Mitochondrial topoisomerase 3 alpha is a probable cofactor of twinkle helicase in age-related mtDNA recombination. Oh my goodness. Oh. Did I just like open a can of worms here? Okay, curiosity killed the cat. I just Googled this abstract here. How mtDNA replication is terminated and the newly formed genomes are separated remain unknown. Here we demonstrate that the mitochondrial isoform of topoisomerase 3 alpha fulfills this function, acting independently of its nuclear role as a component of the holiday junction resolving BLM top 3 alpha RMI1 and RMI2 BTR complex. Oh my goodness, can of worms opened. Our data indicate that mtDNA replication termination occurs via hemicatenane, formed at the origin of the H strand replication, and the top 3 alpha is essential for resolving the structure. Decatenation is a prerequisite for separation of the segregating units of mtDNA, the nucleoid within the mitochondrial network. The importance of this process is highlighted in the patient with mitochondrial disease caused by biallelic pathogenic variants of top3A, characterized by muscle-restricted mtDNA deletions and chronic progressive external ophthalmoplegia CPEO plus syndrome. Our work establishes topoisomerase 3 alpha as the essential component of the mitochondrial replication machinery and as the first component of the mtDNA separation machinery. Oh, my designer. Alice in Wonderland. Okay, I said it. Curiosity killed the cat. That just about killed me. So don't think this isn't easy for. Don't think this is easy for me either. Oh my goodness. I need to get a drink here. That one just about blew me away. Talk about opening a can of worms as if we haven't opened one already. Goodness. I learned something. Topoisomerase 3 alpha. Okay, another genetic computer then is in the mitochondria. Oh boy. Can you see why I'm confident we're going to win this battle? Do you see the complexity? I mean, if it may be bewildering with all these terms, but if you just think of all the parts and all the connections, when you read the abstract, just think, look at all the parts and connections that are there to make this work. It's amazing. And as you go from one can of worms to another, there are just more. But look at it this way. It's not really, in a sense, it's conceptually a can of worms for someone trying to learn this. But it really is a bigger can of worms for evolutionary biologists to try to explain this. So all of this is actually good news. It's just a little torturous in reading it. Okay, so we only got here to D-loop recombination. Oh boy. So let me just scroll up and keep going. Topoisomerase 3 alpha, which is essential for resolution of D-loop recombination intermediates. The centromeric repeats found in an earlier study are most likely ENCODE blacklist sequences, as they lack a strong Z-forming motif. A recent study of the ADAR Z-alpha regulation of fear extinction in mice found that 80%, 97/122 of RNA editing sites overlap with ADAR1 DNA binding with an overrepresentation of sign line elements nearby. Both DNA binding and RNA editing were absent when a loss of function Z-alpha, that's asparagine 175 to alanine, and tyrosine 179 to alanine mutant was tested in vivo assay. This response also depends upon prion formation in the cytoplasmic polyadenation element binding protein CPEB3. Whether Z formation affects memory by altering CPEB3 splicing or the processing of miRNA loci that regulates CPEB3 expression is unknown at present. Since we covered this earlier in the last segment, I'm not going to cover it again. And as Wesley pointed out, can you imagine how long this paper would be if it were written in terms a layman could understand? How about 3,000 pages? I don't think that's under, I think that would be generous. And at that point, if you've read 3,000 pages, you're no longer a layman. But really, on a serious note, you don't have to understand all of this to get the sense. You've got so many connections, so much going on to get this to work. It's just, this is bewildering, and all this in the tiny little, realm of DNA. This is, I wouldn't want to be an evolutionary biologist trying to argue that this is junk, really. That's going to be a losing battle. Let's go on. Let's go, Brandon. ZBP1 Z-alpha dependent functions have been investigated in a number of studies. In mouse models, ZBP1, okay, let me just adjust this. ZBP1 activates necroptosis mediated by RIPK3 MLKL. Okay, so let me just pause a little bit. When you see these short letters like that, like they were just saying R1PK1 / MLKL. that may be individual proteins, and when they put them together, that's a protein complex. Or it could be individual systems connected together. I really want you to get a feel for the number of parts being involved. I mean, again, if you don't get anything else, that's the takeaway. But it's helpful for me to actually see these systems, take accounting of them, and maybe if they're well characterized, that my audience that would be sophisticated, like they might know things like the polycomb repression complex. I could throw stuff like that out. Some of these complexes and proteins I'm not familiar with, but I could tell you that because of Joe DeWeese, at least when I say topoisomerase, people will like, oh yeah, that's the one with the Discovery Institute animation. So if we get more animations for all these other parts, that would be really cool. We need good scientists to explain it, like Dr. DeWeese. Okay, let's go, Brandon. In these studies, tissue-specific gene knockouts were used to induce disease by preventing RIPK1 FADD complex-induced inactivation of ZBP1 RIPK3 kinase signaling through capase 8 activation. All right, it's goodness. This is in my biochemistry textbook, the kinase signaling through capase activation, and I've since forgotten it. Okay, so this, students of biology, that will sound, remotely familiar. Mouse models used epidermis-specific RIPK1 deficiency to produce skin inflammation and intestinal epithelial-specific FADD deficiency to induce colitis. The necroptosis induced was due to Z binding by ZBP1 as either deletion or mutation of the Z alpha domains prevented disease. Let me read that again. The necroptosis produced was due to Z binding by ZBP1 as either deletion or mutation of the Z alpha domains prevented disease. I don't think that's a good sentence, but let's just pause a little bit here and give glory to the Christian God. We should acknowledge him in all our ways. The heavens and highly interconnected specified code of life declare his glory. Amen. And let's resume. Let's resume and let's go, Brandon. Here's a comment. How would they figure out genes for organs, glands, nervous system, or for that matter, even fingerprints? With great difficulty, and I don't think we've completely figured it out yet. And it may not be just the genes, but this non-coding DNA that they call junkDNA might be very important for that. We'll see. So, activation of ZBP1 was by endogenous retroelement expression and dependent on the second Z alpha domain. In skin lesions, signs were upregulated and long terminal repeat elements downregulated relative to normal tissue. Skin lesions were impartially ameliorated by a combination of reverse transcriptase inhibitors, suggesting that DNA-RNA hybrids can trigger ZBP1. Activation of ZBP1 by endogenous retroviruses. Whoa! Activation of ZBP1 by endogenous retroviruses is also reported in human inflammatory bowel disease (IBD) patients, possibly due to low expression levels of the repressive methyltransferase SETDB1. Let me read that again. Activation of ZBP1 by endogenous retroviruses is also reported in human inflammatory bowel disease patients, possibly due to low expression levels of the repressive methyltransferase. So there is a relation that ERVs can have. We don't know if it's good or bad. And if someone could please take care of the bot, that would be appreciated. Otherwise, I'll have to do it myself. In fact, let me log out of my, give me a moment here. I'm going to log out of my other email account so I could take care of the bots. Let's see here. So let me try to take care of the bots here. Sorry for the interruption. There's some really unfortunate things going on with these bots. They serve no utility to society. It's terrible. So thank you, whoever took care of the bot. Thank you, Patrick Alexander. It's nice having a squadron of moderators to defend this channel. God bless you all. So let's continue. In mouse models, okay, let me just scroll up so you can see where I'm starting. In mouse models with selective SED-DB1 knockout in intestinal stem cells, increased levels of ERV in diseased tissue relative to normal was also present. In models of influenza viral infection, where the virus replicates in the nucleus, ZBP1 binds defective viral genomes in immunoprecipitation assays. Although binding to ALU elements or other retro elements was not evaluated. Forced nuclear localization of ZBP1 in this model increased necroptosis, or ptosis. Collectively, these results reveal an important role for ZBP1 and endogenous Flipons in regulating cell death. There are lots of previously active genes that are mostly active before birth. Yes, there are some genes that are only expressed for 3 hours in the lifetime of a creature. That's just remarkable. Only 3 hours, at least as far as we can detect. So ZBP1 seems to be an important protein. What initiates a, okay, so let's just keep reading. I could go off on a rabbit trail and try to find out more about ZBP1, but maybe it's going to be described here. So just, I'll try to file that away. ZBP1 is important. ZB. I just want to point something out. We're throwing a lot of terms here. This is why a protein specialist usually just knows one protein and some of the associated proteins, because it's so complex. There are 20,000, current estimates, there are 20,000 proteins in the human proteome, maybe 500,000 isoforms of those proteins. There's no way humanly possible that anyone would know what they all do. And so the most that we can do is get really good on a few of the proteins to make our arguments. So that's why you'd want a creationist like Joe DeWeese that focuses on topoisomerase. And for those who saw his webinar, it's just mind-boggling because there's so much with just the topoisomerase alone. And what you need is someone to do like ZBP1. And earlier when I opened that can of worms on the topoisomerase 3 alpha, okay, I work on 2 alpha. I saw that 3 alpha stuff on the mitochondrial stuff. I couldn't understand half of what was being said. And like, oh my goodness, like this catenation thing, and I'm just like, oh my goodness, this is serious stuff. So again, I encourage ID proponents and creationists to be very careful not to wander out of specialized fields. Don't debate an evolutionist where he's strong. It's not that we're trying to say that, you know, that what they're arguing is not important, but you have to recognize you have a lot of things you can argue that they're not recognizing as important. For example, I would say eukaryotic evolution is way more important than this human chimp ancestry question, because if you show that there's problems at that level of the tree, the phylogenetic tree, you've cut the tree right at the base. So I'm going to try to end my rant there. So Wesley Coleman asked, I have a question. Erica Gutsick-Gibbon talked with Dr. Gunter Beckley about how a large portion of mouse DNA can be chopped out of the mouse in the population unaffected. Do you have an explanation for this? Yes. Good question, Wesley. Another stupid evolutionary way of looking things. Retarded. Goodness. And creationists keep letting them get away with it because they just don't know. I'm really more angry that the evolutionists do not think deeply and they'll throw this stuff on the table. If they were being responsible, they'd cite the experiments that point out there are many single knockout experiments. You don't realize how important it is when you do a double knockout experiment. And what do I mean? See, I told you I have a short trigger when it comes to science. That is junk science on their part. I'm not blaming Erica for citing that. She's just repeating the garbage that has come out of the evolutionary community because they don't think. Gets my goat. So nothing against Erica here. She cited it. You can knock out the spare tire of your car. Do you know that? You can bore a hole in it. The car functions fine. It's not so good when you need that spare tire. The space shuttle has 5 fully redundant navigation systems. Any one of them on their own could bring the space shuttle back home. And so they have 5 levels of redundancy. If we used evolutionary stupidity, they'd say, you don't need those 5, you just need 1. So let's knock out 4. That proves they're useless. That proves they're junk. That's evolutionary reasoning for you. What we had found experimentally is you could do, Brenda Andrews did a good job of this, and there was another one. You know, now that you bring it up, Wesley. I brought this up. I have an article. See if it's still up. I should resurrect this. Airplane magnetos. Okay, I'm going to put this in the chat. Boy, that thing she quoted just makes me steam. Put that in the chat there. Anything gets my goat, it's that. Okay, so airplane. Okay, so let me just read something. So again, we got that thing with the space shuttles. I gave here an anecdote where I was on the taxiway and one of my magnetos failed. So in the engine, in the piston area, there are in a car, you have one spark plug that gets the piston going. You know, when it sparks, it ignites the fuel. Engine is critical for life in an airplane. See, like if your engine quits and you're driving, you can pull over. You have a chance to just coast and pull over safely. In an airplane context, if your engine quits, that's really much more severe consequences. So with the two magneto system and then two spark plugs, if one of your magnetos fails, there's an electrical failure or some other failure, the other one can pick it up. So they're basically two spark plugs systems and then two magnetos independently using to ignite. I think they had realized, you know, there's a saying that procedures are written in blood. It's because people died. Then you realize, oh, we need to put that redundancy there. So either magneto would be sufficient to keep the engine going if one failed. I was on the taxiway doing a run-up engine test, and I could tell that my magnetos were failing, and I had to take care of that problem by running the engine at very high temperature to burn out all the gunk, burn it off, and then I could get the magneto to run. So what we want is redundancy. Redundancy. And there's a lot of genetic redundancy. There's a lot of redundancy in the non-coding regions. And that's why I flip out when I hear studies like that and they don't complete the story. This is so misleading. They are so eager to tell a false narrative that they'll ignore other studies that point to the redundancy in the genome. It just gets my goat. They're pushing this garbage here, and I could cite studies. I could cite so many studies. And I'm not faulting Erica for not knowing them. I'm faulting the community for being a little too biased, that they just put blinders on their eyes. Gets my goat. So what in that article did I talk about? So I said I was talking about redundancy. And I said here, okay, I cited this minimal genome study. And I'll just read it here. And this is important because this will come up in the junk DNA argument. And, tomorrow they might just throw that, oh, we were able to cut it out and the creature lives. That's exactly the problem with your thinking. It says here, okay, this is from a news report on a New Scientific article. Previous attempts to work out the minimal genome have relied on deleting individual genes in order to infer which genes are essential for maintaining life, said Professor Lawrence Hurst from the Department of Biology and Biochemistry at the University of Bath. This knockout approach misses the fact that there are alternate genetic routes or pathways to the production of the same cellular product. When you knock out one gene, the genome can compensate by using an alternative gene. But when you repeat the knockout experiment by deleting the alternative, the genome can revert to the original gene instead. Using the knockout approach, you can infer that both genes are expendable from the genome because there appears to be no deleterious effect in both experiments. So they'll knock out one gene, it reverts to the other gene, just like with the space shuttle. Okay, and then all right, so you repeat the experiment, you knock out the other gene, and it seems to work fine because it reverted to the first, to the first gene. And again, go to that space shuttle example. What they did is when they knocked out both genes, then it stopped. And that was an embarrassment. I mean, this was horrible evolutionary logic at play. There has since been more experiments like that done by Brenda Andrews. She did it with yeast, and she found similar results. She knocked out every gene in the yeast, and she said almost all the time I could knock them out, and it didn't have an effect on reproductive success, reproductive abundance. They call it fitness. I hate that word, the way the evolutionists use it. It's reproductive. They shouldn't use that word, but they like playing rhetorical tricks, mislabeling things, obfuscation, equivocation. So the first round of knockouts knocked out every, one gene at a time. And she was rather shocked. She said, we could knock out just about every gene individually, and it seemed to not knock out the organism. However, when she started doing combination knockouts, 2 at a time, which is a much more combinatorial problem. So let's say the genome has 4,000 genes in a yeast. I think that's approximately the right number. I could be off. Don't quote me on that. To do dual knockouts, all the combinations, you'd have to roughly do 4,000 times 4,000 to do dual knockout experiments, which is much harder, because what would that be? What, 4 million? 16 million experiments that had to be run. They had a robotic assay to do that. That was just brutal. I think the knockouts were done with some sort of RNA inhibitor or something. It's very hard to actually just re-engineer the genome directly. And she said she needs to do triple knockout. She brought these results to the ENCODE conference of 2015, the ENCODE planning conference, not the ENCODE users conference. I was part of the ENCODE users conference that year, 2015. But the ENCODE planning conference, where you had all the bigwigs, she was there, and she said, be very careful trying to infer function about regions because of redundancy. So in these yeast, you had redundancy 2 or 3 levels deep. She said, if I recall correctly, it could be 5, 6 deep in humans. It could be much deeper. And so these knockout experiments that Erica is referring to, it's like, okay, has this happened? Are you testing this under stress conditions? You have no idea what's going to happen. What we found in Lenski's experiments is, oh, we're killing the genome. Okay, why don't we cite Lenski? We were degrading the genome, and it actually improved reproductive abundance. So that proves nothing. That proves squat. What happened was we degraded its versatility, which means it ends up getting specialized for that environment at the cost of it being so specialized it's going to fail in other environments. So this whole stupid evolutionary definition of fitness in terms of reproductive abundance, that's my answer to what you brought on the table. I don't fault her for that. It's the whole industry's self-delusion and misunderstanding. But what's happening now is we're getting enough experiments that if they're just willing to look at it with a little bit more, just a grain of a little more critical thinking, they'd see it's not making the point they think it's making. And so since I have my junkDNA talk tomorrow, thank you, Wesley, because I expect they'll put this on the table and I need to have a response. So I'm just looking at the article I wrote. I hope you enjoy it. And that website has just gone down tubes as far as they have so many advertisements now. I don't know how they had advertisements for all sorts of clothing there. And I'm not a girl even. They just have pictures of like fashion. If you visit the website that I linked to on my old article on airplane magnetos, we have much more experimental stuff today. The recessive dominant thing is not the same thing, and it's going to be too complicated to explain. So let's just go on. What initiates a change in Z Flipon conformation? The unwinding of bDNA powers the flip from bDNA to zDNA. Enzymes generate this required energy as they work to transcribe RNA. Polymerases generate negative supercoils and SEs faster than topoisomerase can relax them. God bless you, Joe. Joe DeWeese. Because we keep seeing topoisomerase in these. Aren't you glad now that you're learning about topoisomerases? And I will point out something in this article. I know it may sound thick to the uninitiated, but there are at least a few terms that keep coming up over and over. You'll hear topoisomerases and polymerases and the different classes of RNA. It's not that hard to learn, and then that'll open up a lot. So just be grateful that we've talked a lot about topoisomerases on this channel. And you could watch a 5-minute video, which I would recommend, which they have now put up on Evolution News. And you can learn about it. And you could learn a lot about some of these enzymes that, if you just go through the paper and you look at all the enzymes that are mentioned or proteins mentioned repeatedly, just look them up if there's a video. It might be as short as 5 minutes to learn how it works. And then you'll understand the paper so much faster. That's the blessing of Google. Yeah. And Wesley says, wow, I knew that engineers make duplicates of parts or reinforced parts so that they are either replaced if they fail or sustained if they're under pressure. Anything that's life critical, you want to do that. And so in the example of the magnetos, that was really important in the airplane. And I remember I had to make a choice. Am I going to fly on one set of magnetos or not? Or am I going to try to get this repaired? And I really wanted to fly back home. And I said, you know, I had some passengers. I had a responsibility to make sure my magnetos were working. And thankfully, I was trained on how to clear up the gunk in the magnetos. Yeah. Even coding works similarly. I'll tell you where it's even more important is implementations like Bitcoin, where you have distributed network processing. There's no central processing unit. It's exactly for the sake of redundancy that you don't have a centralized computation. It's distributed. And if you knock out some of the Bitcoins or they get corrupted, the Borg collective, so to speak, is able to hopefully fix itself. So let's just keep moving through this. The negative supercoiling they produce accumulates upstream of the polymerase and stabilizes the left-handed conformation. The left-handed conformation is, I believe, the B DNA. Mats, what's YOLO? YOLO? What's YOLO? All right, so you only live once. Oh, NSC is highest at the transcription start site where zDNA forming sequences are found. Negative supercoils, okay. And so topoisomerase relaxes negative supercoils too, okay. NSC is the highest at the TSS, which is the transcription start site, where zDNA forming sequences are found. zDNA forming sequences are found. Okay, the topoisomerase 1 activity here is lower, as judged by the camptothecin, as judged by the use of camptothecin to trap catalytically active enzyme on DNA, even though levels of the enzyme are much higher than in gene bodies, as judged by ChIP-seq. Okay, ChIP-seq is the experimental technique. These efforts are enhanced when upstream DNA is anchored to limit their dissipation along the helix. These effects are enhanced when upstream DNA is anchored to limit their dissipation along the helix. Anchoring can be either by scaffold attachment or by DNA. RNA hybrid formation. Let's see. DNA RNA hybrid formation. The energy stored in the negative supercoils, the NSC, and the zDNA is then available for assembly of transcriptional complexes to load RNA polymerase to the promoter. I'm trying to process this. Okay, so the question is, what initiates change in Z-Flipon conformation? The unwinding of bDNA powers the flip from bDNA to cDNA. Okay, so that's what powers it. We have to know what initiates it. Enzymes generate the necessary and the required energy as they work to transcribe RNA. Polymerases generate negative supercoils faster than topoisomerases relax them. The negative supercoiling they produce accumulates upstream of the polymerase and stabilizes the left-handed conformation. NS negative supercoiling is highest at the transcription start site where zDNA forming sequences are found. The topoisomerase 1 activity here is lower, as judged by the use of camptothecin to trap catalytically active enzyme on zDNA, even though levels of enzyme are much higher than in gene bodies, as judged by ChIP-seq. These effects are enhanced when upstream DNA is anchored to limit their dissipation along the helix. I don't know what these effects are referring to. Okay, I'll just move on. Anchoring can be either by scaffold attachment or by DNA RNA hybrid formation. The energy stored in the negative supercoil and zDNA is then available for assembly of transcriptional complexes and to load the RNA polymerase at the promoter. Oh boy, okay. So, I don't know, okay. This paragraph is not entirely clear what's going on here, so I'm just going to move on. I'm just trying to think in my head. Oh, here it is. The last sentence. There's energy stored. Okay, this is biophysics now. Oh my goodness, this is going to be painful. This is biophysics. A lot of physics is concerned with energy, like potential energy. A very easy example of potential energy is like a spring. So when you coil things up, coiled spring, and you compress it, you stored potential energy. So what's happening is, speaking of coils, DNA can actually, okay, so you can, okay, when you're winding your watch, oh boy, this is going to be painful. Oh yeah. It is already. Okay, the old, I guess like the Swiss watches, they were powered by springs. And when you're winding, some of these old watches, they're really kind of cute. I don't know if they make them anymore. I would imagine they get more expensive because they're easier to make. Digital watches, they're cheaper. And so these things are more of kind of a novelty, I guess, at this point. I still have some of these wind-up watches. So you can either store energy, the potential energy, by winding it up. So the spring, you just wind it tighter and tighter, and you store potential energy that way. Or you could compress the string, or something of both. In this case, you can store the energy kind of in the spring, like a negative, what they call a negative supercoil, or in the zDNA conformation. That's clever. This is like a Swiss watch. You're storing potential energy. So the polymerase, if you ever see the video that, of DNA transcription, you see these little machines just kind of moving down there. But all that energy being pumped as these things are just zipping down the DNA, they're actually transferring energy and winding it up, winding another part of the DNA. So as they're unwinding one part of the DNA, they're winding up the other part and transferring the energy. So as you see a pendulum and a clock, and that's a whole hour of physics lecture talking about the pendulum on those grandfather clocks, the energy is being transferred, from right to left. It's potential and kinetic energy. Okay, it's an hour-long physics lecture. So what's happening is you're getting a lot of clock-like action here. It's really cool. So that's the biophysics of what's going on. So these ALU elements then, oh, this is going to be killer. These ALU elements are able to use the Z conformation to store energy. You see, that's evolutionary biologists for you. They're not biophysicists. They should just butt out of the argument. They're saying it's functionless. I'm like, duh. I mean, if you have so many, if you've looked at like a Swiss watch, you'll have gears and springs all over the place. And just because they look alike, it's like they're junk. You basically have all these spring coils all over the place in the genome, and they're storage elements for energy to do this transcription. Yeah, see, you got it right here. So when I make my presentation to the, obviously ID friendly, they're not all creationists, they're ID friendly faculty. There's some that are evolutionists like Michael Behe, in the sense they believe in common ancestry, but they believe in the design argument as well. There are some old Earth creationists, some agnostic as far as the age of the Earth, and there's some young Earth creationists there. And I'm going to present and say, okay, I'm going to say clock storing energy, springs. So ENCODE was saying the ALU elements are transcribed, therefore it's functional. What did I say about attacking the evolutionary argument from where they're not expecting? This is one of them. Because a lot of creationists, I was on the show with Dr. Dan, and I said, Dr. Dan, I actually agree with you. And this was only, a mere year and a half ago, and I caught flack for agreeing with him. And like, well, what's the problem? Because it's like, you want to debate and humiliate him. It's like, no, I want to get down to the truth. We obviously disagree, but, this isn't for theater. My audience is not trying to win over, people that came for theater and hope to resolve the issue in one debate. My audience are Christian faculty, and a lot of them, this is not their specialty. Even Joe DeWeese, his is topoisomerase. He doesn't really work with ALU elements. I got recruited for that job by Dr. Sanford because hardly anyone in the ID community specialized in it. So that's usually how things fall on you. It's like the job no one else is doing, it's assigned to you. I mean, that's just how it works. But this was actually a big part. And so I'm going to throw this out and say, okay, this is right off the bat, this is already an explanation for large segments of ALU elements. They're an energy storing device. The evolutionists were rightly pointing out the transcription of the ALU elements into RNAs does not immediately say they're functional. They could just be spurious. And I actually had to say, Dr. Dan, I think you had a good point there, Dr. Dan. I would not immediately say that it's wrong of you to say it's, spurious. We just don't know. I would say it's more correct to say we don't know. And of course, he'll have his side of the arguments. And I said, I got to respect that. The responsible thing is to communicate that. But one thing that no one saw coming was the use of ALU elements to store potential energy in the form of like a spring. And that's why this paper's a big deal. And I'm going to hammer on that, because this could be true of every. ALU elements are overrepresented near the promoter regions. And so now this is making a lot of sense. This is killer. This is killer, baby. Let's go, Brandon. Yeah. So I'm glad now I spent a little more time on this. This is killer. And there are some biophysicists in the audience that I'll be addressing. And oh my goodness, it's going to be so cool. And there are lots of engineers. There are actually several groups I speak to. One of them is publicly known. Some of them are private, so I'm not going to identify. I'd rather they not be identified. But one is publicly known. It's the Engineering Research Group, the ERG of the Discovery Institute. ERGs. I like that, because actually we meant, I think that's an inside nerdy joke because we used to measure energy in terms of ergs. I think that's right. Is it energy? I'm getting on a nerd tangent here, but I got to know that. I don't want to pass on bad information. Erg is a unit of energy equal to 10 to the minus 7th joules. Okay, just wanted to make sure I didn't mislead you all. Erg, I Googled it. Okay. Oh, let's stop this. Okay, so Wesley asks, if we look at what we do know, we don't know a part of the DNA that is useless. Yeah. We don't know of a part of the DNA that is, yes. If we look at what we do know, we don't know of a part of the DNA that is useless. Yeah, so if we look at this, now we have an explanation for a large swath of the DNA. We can't absolutely say it's useless because I just showed experimental evidence is showing this is used to store potential energy. It's a wind-up spring. But the important thing is then you can regulate transcription by either letting the zDNA conform to either transfer energy or prevent it from transferring energy. You now have a regulatory mechanism. This is so cool. This is so cool. Ugh! Man, this is killer. So I can't wait to, I presented, so some weeks ago, I said I presented to Discovery Institute group. It was the engineering research group. And I'm glad I had the rehearsal, the dress rehearsal, because the dress rehearsal was just terrible. And I'm like, this is so clunky that I'll make a terrible impression if I present this way. So, but it gave me a chance to rehearse, iron out the problems in my presentation. And so my 2-hour presentation was shrunk down to 45 minutes. I delivered essentially the same material, but more efficiently, and they loved it. And now, I can prepare my Flipon discussion. So this is going to be one important thing I'm going to point out: the storage of potential and the storage of potential energy that can be converted to kinetic energy. So when you have a pendulum, as it goes up to the top of its swing, its energy is converted to potential. When it goes down to the bottom part of its swing, all the potential energy is now kinetic, meaning it's motion. It's energy in the form of motion. It's now realized, and we're having all this conversion back and forth between potential and kinetic energy. It's being used in the transcription process. This is just unbelievably ingenious, unbelievably. And like I said, evolutionary biologists need to butt out of saying it's functionless. This is not healthy for understanding. You see, if they had their way, they would not really want this exploration to continue because they insist it's useless. This also tells us that the sequences, remember, this energetic conversion happens because of the sequences. It will not adopt Z conformations to store energy if it had the wrong sequence. This is where the sequence of DNA actually has biophysical properties. And I did mention that to Dr. Dan. I said, it's repetitive and I think it has a biophysical property. And he was like kind of dismissive. And I grant him that it's like, well, we just didn't know. And to be charitable, I just want to say, Dr. Dan, we just don't know. And he said, he was right to say until you prove it, we're not under obligation to believe it. And I'm just like, he didn't say that literally, but I understood where he was going. And I want to grant him that. But this is, we debated this 2 years ago, and I was not aware of these developments. And even if I were, I wouldn't have had time to talk about it. Look how difficult it is to describe the role. Most of that audience that was listening to us, this is way over the head already when I was talking. If you saw that debate, people were saying that was nerd heaven, but it was really technical. This is like 3 levels even more technical. Okay, so let me share this. I'm absolutely amazed by the smart enzymes that copy and untangle genes in the cell reproduction. That's topoisomerase. Now I'm finding out that they do even more. If they did things in the wrong order, you'd have garbage. Yeah, no kidding. Why assume that what we do know is different from what we don't yet understand? Okay, so let's keep going. Let's keep going, and let's go, Brandon. Yeah, baby. You see, there's a gem in all of that stuff. I found the killer. This is serious biophysics now. Because anytime you keep hearing about energy and storing and converting, that's biophysics. The energetic cost of Z formation in vitro is lowered by the polyamines, such as spermine and spermidine, but not by acetylspermidine or putrescine. Polyamines. The levels of spermine and spermidine are varied during the cell cycle and increase during oxidative stress. Okay, I think those are specific amino acids. A polyamine, I think, is a nucleotide. Wesley saying, I get a chuckle when you say that, Sal. Yeah, let's go, Brandon. Okay, so this seems important enough. I want to just pause. So let me look up what is, I think a polyamine is polyamine. A polyamine is I think Joe insists I use the word amine, not amine. Anyway, a polyamine is an organic compound having more than 2 amino groups. Alkyl polyamines occur naturally, but are also synthetic. Okay, so there are 2 amino groups. I thought they were amino type things. And spermine, what was the other? It was called spermine and spermidine. Spermine. Spermine is a polyamine involved in cellular metabolism that is found in all eukaryotic cells. The precursor for synthesis of spermine is the amino acid ornithine. It is an essential growth factor in some bacteria as well. And Antony van Leeuwenhoek first described crystals of spermine phosphate in human semen in 1670. Okay. All right, I'm sorry I asked. Curiosity killed the cat. All right. I'm sorry I had to be curious how it was discovered. Spermidine is a polyamine compound found in ribosomes and living tissues having various metabolic functions within organisms. It was originally isolated from semen. Okay, I'm sorry I had to ask. Oh boy. That's why I don't want to be a lab or field biologist. All right. Enough said. Let's move on. All right, let's go, Brandon. All right. The levels of spermine and spermidine vary during the cell cycle and increase during oxidative stress, with catabolism due to acetylation by spermidine or spermine N1 acetyltransferase, SAT1. Okay, sorry, these chemicals just have long names. So there's this enzyme called, the way you know it's an enzyme, it has the prefix ACE. So N1 acetyltransferase. Polyamines exist in cells as nuclear aggregates, NAPs. I don't know why it's called an NAP, nuclear aggregates. In vitro, NAPs can promote Z formation and form higher order structures that wrap around DNA to form fibrils. The biological role of fibrils is not clear. One untested possibility involves a role in the production of neutrophil extracellular traps. Neutrophil extracellular traps, nets. Nets are made of chromatin structures from neutrophils extruded into the extracellular space as the result of pyroptosis, which is induced through ZBP1 interactions with RIPK1 and dependent on NF-kB activation of the NLRP3 inflammasome pathway. The nets are stabilized by chlorinated polyamines and are pro-inflammatory. In principle, NAPs could activate ZBP1 by promoting zDNA formation and lead to net formation via gasdermin. Yeah. The way you know it's an enzyme is it ends with the suffix. Did I say prefix? I'm sorry, Wesley. Suffix. Suffix. Sorry about that. Sorry to the viewers. Thank you, Wesley. I got it backwards. Sorry. In principles, NAPs could activate ZBP1 by promoting zDNA formation to lead to net formation of gasdermin. A similar outcome could account for a rare monogenic form of systemic lupus erythematosus, SLE, a disease in which anti-zDNA antibodies are frequent. In two multiplex families, an X-linked recessive form of SLE was due to SAT1 loss of function variants that would be anticipated to increase spermidine levels. In general, NET degradation is impaired in SLE and increased risk of lupus nephritis. Whoa. Thanks, Wesley. But you said suffix, and I was incorrect. I kept saying prefix. Thank you. I actually didn't know the word off the top of my head. I was suffering from Joe Biden confusion there. Let's see, we're going on 1 hour and 53. This is almost 2 hours long. Let me just take a little, I need to get some tea. But this last paragraph was brutal. There are a lot of terms I did not know. And I think I'd like to Google through it and talk about it. And as I said, I'd be doing this anyway, but I figured I'd put it on the net just so people could see. So I'm going to do a quick commercial break. I'm just going to get some tea, and I'll be right back. burning my hand. I warmed my tea. All right, so let's go look through this. And this is how we learn, and it's brutal. Okay. So going back in the paragraph we just read, it said the energetic cost of Z formation in vitro is lowered by polyamines or amines as spermine and spermidine, but not by acetylspermidine or putrescine. Putrescine is it's a smelly amino acid that happens when something's dying. When something's dead and decaying, I'm sorry. The levels of spermine and spermidine may vary during the cell cycle and increase during oxidative stress. With catabolism due to acetylation by spermidine, spermine, N1 acetyltransferase, SAT1. Polyamines exist as nuclear aggregates. So when they say it's a nuclear aggregate, that means that these chemicals that they just identified are inside the nucleus. Okay. And they just listed them: putrescine, spermine, spermidine. Okay. And they said that the polyamines the cost of Z formation, the energetic cost, is lowered by polyamines. Okay. The levels of spermine and the levels of spermine and spermidine vary during the cell cycle, increase during oxidative stress. With catabolism due to acetylation by spermidines, spermine N1 acetyltransferase, SAT1. Polyamines exist as nuclear aggregates. Okay. Let me try to uncoil this. And I'm sorry I have to eat while I do this because my throat is just getting a little sore from talking so much. And also I'm just a little hungry. So this thing that they call junk DNA, the Alus, is, like I said, it's acting like a spring. It's winding up, it's going into the Z conformation and storing energy. But now it's saying the cost of making it form. Okay, so in a pendulum, you're having a nice transfer of cost from the kinetic to the potential energy. But if you add too much friction there, you increase the cost of converting the kinetic to potential energy. All right, so there are all sorts of inefficiencies you can add or remove. And so the way I'm reading it here is the presence of these polyamines like spermine and spermidine can kind of make the process be a little bit more efficient. It lowers the energetic cost. Right. It makes it easier for it to go into this zDNA conformation. You don't need as much energy to make it in that conformation. So it can, okay, so just like a light switch, you do need a little bit of energy when you're pushing it in one state to the other, you know, up or down, or left or right. And, you know, some switches, you have to really, you know, some of the old style switches that were really big, you had to use a little bit more strength, energy to flip it from one state to another. And sometimes you don't need as much. So as we have these polyamines inside the nucleus, it'll lower the cost. And this will happen when we have oxidative stress, or it varies during the cell cycle. So this is really cool. We can prevent the switching on and off. So there's a pathway to regulate the switching on and off. Does potential energy take energy to store? The answer is yes. Now, there's a subtlety here. It's like, well, when you have the universe, does it already have potential energy? And it's like, yeah, oh my. Okay. So I'll say a qualified yes. How about that, Wesley? Take care of the bot here. Got him. I zapped him. And there are various forms of potential energy. I think chemical energy could be said to also be potential. I have to talk to a physical chemist about that. Well, okay, let's go to the first law of thermodynamics. Energy is neither created or destroyed. And so potential energy has to come from somewhere. So one form of, you're not destroying energy, you're just changing from one other form. So does potential energy take energy to store it? Answer is yes. First law of thermodynamics. Yeah. Now, did potential energy exist at the original creation? I'd say yes. There's potential energy between the moon and the earth, for example. Okay. So let's just amend this. Does potential energy take energy to store? Yes, or an act of God. All right, how about that? That's a good question. And that makes me think about physics. So now you're getting a taste of biophysics here. This is some really good biophysics right here. The amount of experiments they had to run and the amount of thought they had to do to make these conclusions about the energy levels. This is tough stuff. You know, I'm just kind of researching it from relying on other people's research. But the guys that actually had to run the experiments and do all the calculations, that's the heavy lifting. That's the serious biophysics right there. So let me just look a little more. Okay, so they're using some terms. Okay. They're using a term I'm not familiar with, fibrils. Okay. I know why I was confused. There are lots of places that use the word fibril. And it's not limited to DNA only. Okay, so fibril, DNA fibril. Fibrils are composed of linear biopolymers. So let's just read this. Fibril. Fibrils, from the Latin fibra, are structural biological materials found in nearly all living organisms. Not to be confused with fibers or filaments. Fibrils have diameters ranging from 10 to 100 nanometers, whereas fibers are micro to mini scale structures and have filaments, and filaments have diameters approximately 10 to 50 nanometers. That's not very helpful. Fibrils are not usually found alone, but rather are parts of a greater hierarchical structure commonly found in biological systems. Due to the prevalence of fibrils in biological systems, their study is of great importance in fields of microbiology, biomechanics, and material science. And here they have a picture of amino acids, fibrils made of amino acids. And so, yes, I've seen fibrils in the context of collagen, which is one of my favorite proteins. But they don't have, yeah, I've talked about collagen a lot, so that's why it sounded confusing. DNA. See, here in the Wikipedia article, it doesn't have anything about DNA fibrils. So this is a different usage than what I'm accustomed to. So let me try to uncoil this again. We have these polyamines with the spermine, spermidine. They aggregate together and they wrap around the DNA and make fibrils. So you basically have the DNA and polyamine structure. And this is just mind-blowing because when you have pictures of DNA in the nucleus, you just think that DNA is just floating around by itself. It's not. They're constantly all these chemicals around the DNA, all these molecular machines, and they're using the term fibril, which is kind of almost unfortunate because we tend to associate fibrils with collagen. And yes, Wesley would find collagen. So I just have to point out, let's just be cautious here. We're not talking about collagen fibrils. This is a usage of fibrils that is the first time I've seen it. And it might be very unique to this literature. It's not used in the same way. So just be careful. That's the way I'm reading it. The biological roles of fibrils is not clear. One untested possibility involves a role in the production of neutrophil extracellular traps. Nets are made of chromatin structures from neutrophils extruded into the extracellular space as a result of pyroptosis, which is induced through ZBP1 interactions with RIPK1 and dependent on NFK kappa B activation of the NLRP3 inflammasome pathway. Oh my goodness. Okay, I'm going to have to uncoil that, which reminds me though, let me just look at the references for this energy thing. Okay, they have reference 88, 94 through 96. I think those are important enough. We need to look at that. So I'm going to just back up a little bit and go to those references. So what is a neutrophil? Neutrophil. Another can of worms could be opening. So let's look up neutrophil. Neutrophils are a type of white blood cell. They make up the biggest number of all kinds of white blood cells. They kill and digest bacteria and fungi to help your body fight infections and heal wounds. And again, we have to be very careful if it's using that word in the same way here. Okay, so these fibrils in the nucleus are very important for creating neutrophils. Neutrophil the extracellular traps in neutrophils. And neutrophils are white blood cells. Nets are made of chromatin structures from neutrophils extruded into the extracellular space. Whoa! Whoa! You're getting chromatin out of the nucleus. Let me try to adjust my camera here. We're getting chromatin out of the nucleus and putting it in the extracellular space. This is nuts. Awesome. We're taking stuff in the center of the cell and putting it outside for a purpose. Let me read that again. Nets are made of chromatin structures from neutrophils extruded into the extracellular space as a result of pyroptosis. Dang. See, guys, this is the way to argue against evolutionary biology. You study stuff that they don't. Why do you want to argue the bird dino transition? This is so much better. Pyroptosis. Pyroptosis represents a form of cell death that is triggered by pro-inflammatory signals and associated with inflammation. This type of cell death is seen primarily in inflammatory cells such as macrophages and may be triggered by bacterial or pathogen infections. Okay, from nature. Pyroptosis, host cell death and inflammation. Life or death of individual cells determines health and disease in multicelled organisms. Cell death is crucial for organogenesis in utero and successful control of host cell populations in healthy tissues. It can also play a part in disease that occurs in response to toxic insults and microbial infection. Okay. Organogenesis. Okay, we go down the rabbit hole into Wonderland here. Organogenesis. Organogenesis. I think that's just the making of organs. Organogenesis is the phase of embryonic development that starts at the end of gastrulation. Okay, it's a phase of embryonic development that starts at the end of gastrulation and continues until birth. During organogenesis, 3 germ layers form from gastrulation: ectoderm, endoderm, and mesoderm, form the internal organs of the organism. Wow. Okay, so going back to the paper, one untested possibility involves a role in the production of neutrophil extracellular traps. Nets are made of chromatin structures from neutrophils extruded into the extracellular space as the result of pyroptosis, which is induced through ZBP1 interactions with RIPK1 and dependent on the NF-kappa B activation of the NLRP3 inflammasome pathway. Okay. This means, okay, they've said it's still untested, but the hypothesis is that the junkDNA is actually controlling this inflammation response. It's taking chromatin, DNA chromatin complex from the nucleus, putting it out there, and it's creating a inflammation response. This is incredible. This is using DNA in ways that's way more than coding and gene regulation. It's using it as biological signaling between cells, which is just like unheard of, because we normally think of it as contained in the nucleus. It's throwing this chromatin out into the extracellular space, and it's being used as a signaling mechanism. It's unreal. Ugh, my head's exploding. So now I do want to go back, because this whole thing about the springs in a Swiss watch is important enough. I want to look at the references. And so reference 94 through 96. As if to open another can of worms. How about a rabbit hole into Wonderland? Okay. Oh, wow. He's referencing some really old. Let me show it to you guys. He's referencing some really old papers here. We have to be careful. (2004). Okay. Hey, David. I'm trying to do a journal reading here. This is really thick stuff. I want to look up this reference here. Distributions of zDNA and nuclear factor in human. This is a forgotten paper. An analysis of the human chromosome 22 genomic sequence shows that both zDNA forming regions, ZDRs, and promoter sites for nuclear factor 1 are correlated with the locations of known and predicted genes across the chromosome and accumulate around the transcriptional start sites of known genes. Thus, the occurrence of zDNA across human genomic sequence mirrors that of known eukaryotic transcription factor, of a known eukaryotic transcription factor. And that is nuclear factor 1, nuclear factor I. In addition, 43 of the 383 fully annotated chromosomal genes have ZDRs within 2 nucleosomes upstream of strong NFIs. This suggests a distinct class of human genes may potentially be transcriptionally regulated by a mechanism that couples zDNA with NFI activation, similar to a mechanism previously elucidated for the human colony stimulus factor promoter. The results of the study will facilitate design of experimental studies to test the generality of this mechanism for other genes in the cell. Oh my goodness, I can't believe that this is a 2004 paper and it's just been ignored. This is a big deal, guys. You know, in this whole junk DNA narrative, papers like this just kind of go by the wayside. You know, like I said, some topics get too much press, like this whole thing about junk DNA. The evolutionary biologist just arguing, and unfortunately, the ENCODE project did give them a little bit of fodder by framing the issue in terms of RNA transcription. But there's a lot of material here in terms of the biophysics. So now I'm feeling good that I'm in the molecular biophysics arena. Not that I would even fancy myself as an actual molecular biophysics experimentalist. I'm just a reader and reporter on this. But this is a big deal. This is a big deal. And it's a 2004 paper. Okay. Look at this diagram here. Oh, yeah. Now we got some heavy lifting right here, too. It's describing, let's see, proposed mechanism for zDNA coupled transcriptional regulation. Okay. So in 2004, they proposed how zDNA can regulate transcription. Okay. And then in 2020, Alan Herbert is throwing out the experimental evidence to that effect. This is a tough paper that Alan put together. He's been following this for a long time. Let me warm my tea and I'll be right back. Oh, and right then, our bot friend shows up. Let me deal with him. Goodbye, bot. So I'll put this paper back up here. And I'll be right back, guys. Need to just throw this in the microwave. All right, I'm back. Hey, Sal, what is your approach for reaching out to evolutionary theists and atheists? From someone who was a proponent of evolution, do you have any insights as to what will open them to persuasion? I actually was not really a proponent. I was a believer in it. I didn't really advocate one way or the other. And this is I was a high school kid. So let me think on that. I think get them when they're very young. Get them looking at the topoisomerase video and thinking, if because there's the complexity. And when I've shown this, some of the stuff like with Rebecca, the research. So it's when they get to the stage that some of their metaphysics and their lifestyle is dictated by evolutionary theory, it's almost too late. Because there are, this is one time where a scientific conclusion, or a conclusion that is affected by our understanding of science, will affect the way we live our everyday life. And the decisions we make, and it's not just the way we live, but you have to assess how you've lived your life. So for someone that's later in life and they've done this all their life, and they've made, say, ethical and value decisions about how they live their life, let's say they were non-Christians, it could lead to a lot of regret. That's hard to face. We do know statistically, at least one study, it could be, it's an obsolete study by now, but I think there's some validity to this, is if you're not converted to being a Christian by around your mid-teens, 90% of the people that are Christians for a long time became Christians before they were 20 or before they graduated college. After that, it's very hard. Now, praise God for the ones that are converted after college. They've been disproportionate, in my experience, those people have been disproportionately influential on Christianity because they've had a chance to live a non-Christian life for such a long time, and then they reject it. So that ends up being a really big deal. And by way of parallel, I think to the extent that evolution has affected the way that they've lived their lives, that, you know, that has to factor. So back to your question is, when they're young and you can reach them with science talk, you know, one thing that does not, I've never seen this work or work well, and it's not been, you know, I don't know one creationist, honestly, that I would consider thoughtful, where he was just beaten down and bullied and say, you will believe the Bible, you'll believe the Bible, you reject that. If they move on to science, that I don't see, I don't know many of them, okay? Nathaniel Jeanson and Joe DeWeese, they were brought up as creationists and they heard the other side. So they have to want it on some level. So like if they have kind of a dissatisfaction with what evolutionary theory can give to them, because the idea of creationism for me was appealing, because if we could show that it's improbable, that's evidence of a miracle, and that was to me very valuable. So I think you have to sense where they are as atheists, because not all atheists are alike. The reason you know that, they're atheists that say they want to believe in God, and they're atheists that said they'd rather go to hell than serve a Christian God. So you have to know where they're at. Yeah, they do a lot of damage. Because what they do in the churches is they said, well, creationism isn't important. You can believe in God without believing in creationism. What you forget, though, is if you believe in creationism, that'll help you believe in God. So I had a video, Richard Lumsden, he became a creationist first and then a Christian. His science said there had to be a creator. It started to convict him. He said, okay, his science said evolution's wrong, therefore life was created. 6 months later, he said, well, that if life is created, there has to be a creator. And you could tell he was wrestling in his heart. And then he answered the altar call. So I think they do a lot of damage in the church because they put up enough of a fuss that a lot of pastors say, well, I don't want to, I want to keep unity in the church. I don't want to talk about a controversial topic that'll divide people. And therefore creationism's not even taught. Or let's say debate it. How about debate it? It's like, no, we don't want people arguing. What I think is unhelpful is when the creationists make this a salvation issue, where they start to demonize theistic evolutionists. Thankfully, my path was not that way. No one pointed a finger at me in church and said, you're somehow sinning because you believe we evolved from apes. I didn't have that done to me. And I would not do it to a theistic evolutionist. To me, that's repugnant to do that. That's if they're just a simple believer. If they're a professor of this, if they're Joshua Swamidas, I'd get in their face. All right. So it depends on their station in the church or their position. If they're a position of influence and respect, and they're real like advocates and promoters like BioLogos, oh yeah, I'd fight tooth and nail. I'm not into about persuading them. I'm into stopping them from damaging people's faith. Because, like, for example, Francisco Ayala, ex-Catholic priest, and he was saying, look how stupid biology is put together. You know, the intelligent designer must be incompetent. And I read the whole essay that he wrote. It was powerful in kind of a dastardly sort of way, if you know what I mean. And what we're reading now is just ripping into shreds. I mean, this is like me celebrating in the end zone. I would get so many unsportsmanlike conduct penalties if this were football, because I'm just rubbing it in that people like Ayala were wrong. And I think he would identify, at least at some time, as a theistic evolutionist. And he did a lot of damage. And I think Swamidas is doing a lot of damage. And a lot of these theistic evolutionists, they're doing a lot of damage because they're trying to say, oh, let's just not debate over this. Or, you know, we can all be together and believe in God. I'd say this, some of you might, not everyone. Some people, it might mean a lot to them to know that life is miraculously created, because that would also mean we're extremely special based on the scientific evidence alone. So let me just highlight. So, you know, it depends on where someone is. You know, for that high school student that's just learning this in school, I want to show a lot of grace toward him. But to people I perceive to be kind of sketchy in their arguments, I'll get in their face. So it depends, you know. They'll say this is great science, and I say, well, look at Ayala. His call on Alu elements is a disaster. How can you call that good science when it keeps making stupid predictions about what we'll discover? So, and then it's destroying people's faith. Sorry to be eating. This is a long session. We were going through some of the supporting papers, and Wesley and God Teach Me to Pray Your Word, thanks for joining this. You've made this a lot more exciting. So we had this paper here. Good point. So that was reference 94. We have another reference, 1992, and another reference in 2001. Okay. These are forgotten references. I want to see how he got into the energy transfer discussion. Okay. I'm sorry, I'm just, I'm silent, I'm trying to read through this. Okay, so they're talking about zDNA at the transcription start sites. That's 94 through 96, old stuff. Let me go back up here. I'm sorry you can't see my pointer too well. I try to, hopefully you can sort of see it. I'm trying to see where they say there's energy transfer. Okay, so there's a little bit of a weakness in his reference trail here, just a little misleading. I wouldn't say it's a horrible fault, but it would have been helpful if he went a little more in how energy transfer, because that's the biophysics part that's of interest. So right here, it's just asserted. I think it's elsewhere in the paper he goes into the energy transfer. So let me just quickly just scan to see if he has an energy transfer discussion. Okay, I'm going to cheat here. I'm just going to do a Google search because I didn't see it as I was scrolling through there. I'm going to do Google search. zDNA energy storage. All right, here we go. The role of zDNA binding domain in innate immunity. All right, maybe we got something here. Frontiers of immunology. Both DNA and RNA can maintain left-handed double helical Z conformation under physiological conditions, but only when stabilized by zDNA binding domain. After initial discovery in RNA editing enzymes, ADAR1, and by the way, I reported on ADARs in Contested Bones in Dr. God willing, soon to be Dr. Roop and Dr. Sanford's book. ZDBD is also describing a pathogen sensing protein ZBP1 and PZK in host, as well as virulence proteins E3L and ORF112 in viruses. The host virus antagonism immediately highlights the importance of ZDBD in antiviral innate immunity. Furthermore, zRNA binding has been shown to be responsible for localization of ZDBD containing proteins to cytoplasmic stress granules that play a central role in coordinating cellular response to stresses. This review sought to consolidate current understanding of RNA sensing in innate immunity and explore possible roles of zRNA binding with cytoplasmic stress granules. Holy smokes, there's zDNA and zRNA. Oh my goodness, my head's exploding. Okay, so now let's look at energy. Energy. No. Okay, here it says, under normal physiological conditions, zDNA, zRNA exist at higher energy configuration and thus are energetically unstable on their own. That's the only mention of zRNA energy. Higher energy configuration. I'd say that's higher potential energy. So I would feel more comfortable if there were a little bit more data on the energy state. And how it can transfer. I don't think that that's been really, it's either assumed that this should be obvious. I would just feel a little more comfortable if there are more peer-reviewed literature that's describing the transfer of energy from one state to the other. Now, Joe DeWeese in his webinar was talking about the transfer of energy in the coils and supercoils. And if I have time, I might bug him. I have a meeting with him. I get about 3 or 4 emails from Dr. DeWeese every day because we're working on a paper together. Now, most of the time, I don't have anything to input because it's kind of a group email among our research team. But if we have a meeting, I might ask him if we have the biophysics papers that describe the mechanics of energy transfer. But what he was saying is either that or it was Alan Herbert who was saying that they've been measuring the angstrom distances. And so you could tell if there's been an energy, nerd flex. When you're pulling it apart, if there's kind of a springy energy there, or if you're coiling it, there's energy result. And these were tough experiments to do. A lot of biophysics in analyzing the energy states. So let me just see this. So instead of energy storage, I'll say energy, just cDNA energy state, or cDNA. Holy smokes. This is 2020. Oh boy. Oh, let's look. And I'm running out of gas. This has been too much fun. Deep learning approach for predicting functional zDNA regions using omics data. Computational methods to predict zDNA regions are in high demand to understand the functional role of zDNA. The previous state-of-the-art method, Z-Hunt, is based on statistical, mechanical, and energy considerations about B to zDNA transition using sequence information. Oh my designer. Statistical mechanics. That was a tough class. Statistical mechanics and thermodynamics. This is serious. This is serious science, biophysics, nerd torture. Adding epigenetic and other functional genomic markups to DNA sequence sequence level can help revealing the functional zDNA sites. Here we take advantage of the deep learning approach that can analyze and extract information from large volumes of molecular biology data. So they need a lot of high-powered computing to find the zDNA stuff. After discovery of a standard form of DNA, which is the canonical right-handed B form, I'm sorry, I got it backward earlier. I said the B form's left-handed, it's right-handed, or bDNA. Other DNA configurations were found to exist. One of them is left-handed DNA, termed as zDNA. Okay, I got that totally backwards. Apologies to the reader. Investigation of the crystalline structure revealed characteristic properties of nucleotides in zDNA, irregular alternation of the syn and anti-base conformations along each strand of the helix. Early experimental evidence confirmed presence of zDNA regions in viruses, bacteria, and mammals. Later, zDNA was also found in yeast, fly, and humans. zDNA has diverse functional roles. zDNA has diverse functional roles. And guess where zDNA conformations emerge plenty? In ALU elements, the so-called junkDNA. Oh, this is killer. zDNA located in promoter regions may work as a regulator of transcription. Association of promoter zDNA with transcription was found in c-Myc gene, corticotropin-releasing hormone gene, and ham oxygenase 1 gene, HO1. zDNA was confirmed to act as a repressor in the promoter of ADAM12, known to be overexpressed in many human cancers. All right, I'm just going to go here and see if they have anything more on energy. Z-Hunt algorithm considers the stability of zDNA as the difference in free energy between the right-handed B and left-handed zDNA conformation and employs statistical mechanical approach for B to zDNA transition induced by negative supercoiling. Energetic parameters for dinucleotides associated with B to Z transition were taken from experiments. The analysis of zDNA 1 megabase fragment, containing 137 genes revealed 329 potential zDNA forming sequences. many of them found near the transcription initiation sites. All right. Oh, wait, did I see that? What is that? P.R. Marshall. Who's that? Is that Perry Marshall? Oh, it's Paul, not Perry. I was like, that guy's going to be on Maddox's channel sometime. Okay, so let me try to process this. They were able to establish the energetic states here, and I'm suspecting we would be on good ground to say that what was in the peer-reviewed paper in the Royal Society publication that I'm reading for, Alan Herbert, is probably on good ground. That it's natural for it's like when you drop a rock, it's going from a higher energy state to a lower. It's releasing the potential energy, and it's now in the lower state. The zDNA state is like lifting it. So when it's saying it's in a higher energy state, it's in a higher potential energy state. And when they talk about the free energy, the change in free energy, if it's negative, that means it's losing the potential energy. And that means that's the natural direction for the reaction. So when it's saying that energy is stored in the zDNA and in the negative supercoiling, it's used to help in the transcription process. This is really cool. And then also the zDNA is used as a mechanism of transcription. So, of course, the evolutionists will say, what about all these other creatures, some that have so many long strands of DNA? This is going to be really bad news for the evolutionary biologist. It would appear that each of the creatures use the DNA in very different ways. That would be devastating. So therefore, you have these lungfish and humans that find different mechanisms for using DNA. So like we heard, one of them was in the inflammasome pathway and the pyroptosis. They're just different ways that they could be used. So that means all these things are kind of specially created. That would be devastating for them. And then I addressed the problem of, oh, you can cut out all this amount of DNA and it's still functioning fine. Yeah, we saw that. What do you mean by functioning fine? You've lost versatility. It's been optimized for one environment, but it no longer has versatility under stress response. That's a result of the Linsky experiment. So, why am I reading all this? If we're going to prosecute the case against junkDNA, and remember what's at stake, if junkDNA is functional, then evolution is wrong. That's a paraphrase of the original thing that Dan Grauer said. If ENCODE is right, evolution is wrong. This is going to be devastating. Evolution will be wrong on so many levels, especially as we discover, like, the Alu elements are unique to primates. And it does transcriptional regulation with Alu elements. What about creatures that don't have Alus? They use the DNA in a different way. It's a different architecture. This is really bad for evolutionary theory. It's going from bad to worse every day. And I think the most I could do, because I can't be an expert in this, is to just present this to the engineering group and say, okay, there's so much here, we can't digest it all. But I'll at least make you aware of the literature. Please accept the caveats that there's still a lot of experiments to be done, but this is looking so promising. I'm putting it on the table because we've been beaten down and we're just kind of doing knee-jerk reactions to whatever the evolutionists say. And it's distracted us from reading the rest of the literature kind of in obscure places. Just like some of the papers that I just saw just now, where they talked about zDNA. And I think in Larry Moran's blog, he doesn't have a lot about the zDNA affecting transcriptions. So there are a lot of sequences that can conform zDNA, but Alus are especially good at that, especially good. So I think when I make my presentation, I'll say, okay, there's a lot moving forward. I would not want to be on the Larry Moran, Francisco Ayala side of the argument. It's going to be embarrassing for them as this moves forward. And I can sense already in the professional literature, they're just not caring what the evolutionary biologists have to say anymore. As far as, we have cancer problems to solve. We have other diseases to solve. We want to know how the genome actually works. Quit telling us that it's junk, because it's probably there for a reason. It's not helpful to say that our research into these regions is a waste of money, because we are finding function. That attitude is very negative and unhelpful. Thank you, Wesley. And I'm actually running out of gas myself. I think I might go relax at John Maddox's channel. I'd really like to thank any of the viewers that have watched, all the viewers that have watched this live, the few of us that are here, but especially to those who are taking even a little bit of time to watch this in recording. And it's been a fun night. Take care, and the Lord richly bless you.